All right, good morning, everyone. My name is Michael Simpkins. I am a student at the University of Missouri studying chemical engineering, emphasis on environmental science, business minor. This summer, through the IEPA program, I was located at BASF out in Kankakee, Illinois. Here is a blurred overview of the site. This is 310 acres of facility, but of that 310 acres, roughly 200 is actually up and running as factory. So just a little bit of information about BASF. It is the largest chemical producer in the world. 1865 was when it was founded, headquarters out in Germany, operates in over 80 countries and supplies customers in over 200 countries on top of that. There are roughly almost 400 sites across Europe, Asia, Australia, America, of course, and Africa. We produce a wide range of chemicals, and these chemicals are, anything that can go into producing something major. So, for example, we produce chemicals that go into plastics and, oils, things like that, agriculture. Those are just a few, just to name a few, because we'd be here all day. BASF has a global initiative to improve sustainability, and since they've been implementing this. They've cut back on energy efficiency, saving 19%, water waste management 29.7%, and emissions on air pollutants is down 63%, and this is on a global scale. And then the current standings as of 2014 in relation to the goals for 2020, we're pretty much there, except for right there. And everything else is looking really good. We're on the move. And yeah, air emissions are down, water improvements are up, and energy is doing well. But just a little more information about the Kankakee site and where I was actually located. Like I said, the site is 310 acres. It operates 24/7. There's roughly 240 employees. And this site in particular, we produce primarily three manufacturers, which is EM, and these are care chemicals that generally go into nutrients and vitamins and whatnot. EN, nutritional health, and ED, dispersions and pigments. But just to give you a better understanding of what we do, for example, we produce a lot of vitamin E, and this gets sent and put into different forms of pills, capsules, supplements. We also make resin, which is a heavy dye, heavy ink, and that goes into cardboards and, for example, your cereal boxes to do the coloring for those. And another large one that we produce is surfactants, which is the soap that gives you that texture for your detergents, your hand soap, your dish liquids, that kind of thing. And my immediate supervisor at BASF is Mr. Chad Starr, who is the Senior Site Services and Utility Manager. And this is one individual who really helped me out and guided me through my experience and my journey here at BASF, and I'd like to thank him. He's here today. So this summer, my EPA project assignment was primarily to reduce the use of fresh water, and this is a rather broad assignment, a huge task, and one that I was definitely not ready to take on. But with the help of Mr. Chad Starr, we were able to narrow the scope down and start small, take baby steps. And for example, we started with the water assessment. And like I said, how EPA has global initiatives to improve water and energy efficiency, things like that. We are also doing a wastewater assessment. And it was our turn to do the wastewater assessment. So me and Mr. Chad Starr got moving on that. And so with that, I reconstructed area flow diagrams. And this site has 115 areas. We narrowed our scope down to roughly 21, 23 areas that used majority of the water, like massive bulks of water. So with that, I redrew the flow diagram so we can have a better illustration and see exactly how water is used. We set up meetings with the area operators and discussed exactly what information we needed for this water assessment. I'll go into further detail on that. And with that water assessment also came a water inventory where we kept logs and charted records on how much water is being used where, what is used for, and how the water quality is once it's done with that process. And yeah, like I said, the goal is to reduce the use of fresh water. That was the ultimate goal. And of course, lower monthly utility statements with that. So for example, like I said, I had to reconstruct the flow diagrams. This is one area, area 21 of 115. And I reconstructed this with PowerPoint presentations. So these are a lot of lines, a lot of blocks, a lot of circles and squares. So yes, this is area 2021. It's kind of one large process, and redrawing these took about 2-3 weeks. And here's a chart, an example of the chart we used to do the wastewater inventory. And like I mentioned, we detailed the processes, the water usage, what we're using it for, whether it's wastewater, cooling water, storm water, fire water. In this example, it's just primarily wastewater. And we listed the process operations and the water sources and origins, so where it's coming from, most of it being city water. Some parts we did use stream water and well water. And then the discharge points, and obviously all of those were, well, these C2 bottoms, it's stretched out, so it's kind of hard to see. But ultimately, at the end of the day, with the site, we have a wastewater treatment plant facility there, so everything kind of merges to that one ending point. So it's like a lot of piping, a lot of tubing. It's kind of confusing. It's like a spaghetti bowl, actually. But all the water trickles down and ends up at the wastewater treatment plant. And from there, we purify it, we clean it ourselves. But due to ordinances, we send it back to the city and pay a lot of money to get it cleaned and repurified, and they pretty much send the same water back. I also used a list of hazardous material so we could just keep record on this Excel file of each area. For example, this is area 21, so on this Excel tab, it would show the chart, the hazardous materials used, just so everything is precise and in one location. And again, this is just an example of one of the many areas I did. And with this water assessment, meeting with the area operators, because they provided the chart information with the flow rates and in gallons per minute. They also provided a list of additional water usage at the area location. So these water usages being, general building cleaning systems. And for example, this was a POD system, which is pretty much a liquid separator. So it'll separate two liquids just based off specific gravity and its density. So for example, oil and water that does not mix, put it through there, separate it easily. So this is just one example of additional water usages that we like to keep track on, because ultimately we just pretty much get one utility statement that says this is how much water you've used. But with this water assessment, we now have a better way to analyze and keep track of how much water is going where. In the midst of waiting for area operators to send back information, because a lot of the areas are very intricate and include a lot of details. So to keep myself busy, I walked around the site and went to every area, pretty much. Every area of interest, I want to point out. Not all 115, just like the 21, 23 that we're really taking into consideration. So I walked around to these areas and made, visible observations, noted, here's a leak there, here's another spill here, oh, it's overflowing there. And this is a part of the internship that I really got to utilize Mr. Reese's information from the training. If anyone remembers the bags with the flow rates where you can use for the shower heads and the faucets, found a leak that was shooting out of a pipe. I was able to put the bag under there to capture it and determine how much water we're actually losing by the minute. And it was 0.03 gallons. This is really minute compared to how much water we use on a daily. So that, I mean, that trickles to about, what, $7 a year in just that one spill alone. But some of these areas have 10 or more leaks. Those are the red ones highlighted. These orange ones with the exclamation marks, those were the areas that were just kind of like a mess. It was hard to pinpoint exactly where the leaks were coming from. And the yellow ones are, you know, pretty neutral, like, all right, it's fair, it's respectable. And the green are, you know, little to no leaks. And I like to point out, it's not a bad site. It's not like we're just running operations that nothing works. This is 300 acres, and all year round things go wrong, whether it's too hot outside, too cold outside. Just the weather, the temperatures, the seasons alone will cause some technical difficulties in your operations. And some of these sites or some of these leaks, you'll go back the next day, they're already fixed. So this may not even be accurate anymore, but it's just to keep me busy while we're waiting on information. So one thing I did find is that we do use a lot of water in our cooling towers. So I like to narrow my search to the areas where we did use the most water, and the cooling towers and boilers, of course, were pretty much the bulk of it. And these cooling towers just serve various load purposes. We have 8 towers, and these towers too operate 24/7. And total is about 2,000 horsepower. Oops, I'm sorry. Total is about 2,000 horsepower that's pumped out, and they hold roughly 17,000 gallons per minute. And now, what the problem with these cooling towers is the high cost for cooling water. And so the goal in mind is to minimize the withdrawal of the cooling water from whether it's the river or the city water that we use. And so one solution would be to add an open cooling loop so the water does not run through once. It can cycle and filter itself out. To give you a picture or understanding of it, it would basically be just one continuous loop of water filtering itself through a sand bucket in a way, and being able to reuse that water. And that you would pretty much use only 5 to 10% of the current circulation water that we are using today. And now these numbers may not be accurate depending on the stature of the cooling towers and exactly how they're used and how they're being used, but these are just ideas worth looking at and taking into consideration. And if this were the plan, basically we can drop the water usage tremendously and reduce almost 15,000 gallons a day, which is well over a lot in a year. And this is a lot of water we use on a daily basis. And so this potential saving offers about $11,000, with the cost of water being $2.07 per 1,000 gallons. And this is information I was able to graph and reference from the utilities. I have a whole list of the 2014 utility statements, so I was able to get that information from there.
Is that tower number 5, is that one of the bigger cooling towers you got there? Or?
Actually, I don't even know off the top because just walking around the site, but yes, I do believe it is. It is one of the bigger ones.
It's the biggest.
The biggest, thank you. And then yes, there's, with another portion of the area being of high water usage being the boiler systems. If we were to get in there and try to implement something new and save some water, and one of the ideas I was able to find is to condense the condensate and be able to reuse that. And these ideas were provided in a BASF best practice handbook from the headquarters, and these are all general ideas that the companies share globally. So you can look at it, reference it, see what processes you have at your site, and cross-reference it with ideas that were already implemented. And if this were to be implemented, we can reduce the use by 20%. And that's literally just by recovering the condensate instead of disposing it. And if you were to do that, that would save you almost 50 grand a year just on water usage alone. And that would save, billions of gallons of water again. And like I say, the cost per gallon is $2.07 per 1,000 gallons. And now another mechanism to reduce the use of fresh water was provided by ComEd, outreach professional. And this audit took place a few months or so prior to me arriving, so everything was kind of already mapped out, but at the end of the day, nothing was kind of obtainable just due to the payback period. Everything was kind of far-fetched. But in the findings, there was one mechanism that would slightly reduce the use of fresh water, so I felt like it would be of significance to note it, and that would be to install temperature controls on process heat exchangers. And with this, the heat exchangers are designed to have a 10-degree Fahrenheit temperature differential. Process heat exchangers in the building serve cooling towers 5 and 7. They do not currently have temperature controls and temperature differential of only 2%. So with that, if we were to install these temperature controls and get it to the optimal 10%, or the 10 degrees, you would lower energy consumption tremendously. So, and it would be the equivalent of shutting off one pump, one tower entirely. So yes, this would be the potential to reduce 80% of your fresh water usage here. And then, like I said, the energy you would save would be the equivalent of cutting off one tower entirely. I'm just kind of running through this for the sake of time. So with that, if you were to use it for cooling tower number 5, you can save 80% on the existing conditions, which are initially 3,840 gallons per minute, and you will reduce it by 3,072 gallons per minute. And this was the equivalent of cutting off 2 pumps entirely, and that'll save you 400,000 kilowatts an hour if implemented. And then there's also a mechanism for cooling tower 7 where you can pretty much do the same. And this one, it runs a little differently, so it won't necessarily be as much, but you would save 1,920 gallons per minute. And it's not the equivalent of cutting off 2 pumps, it'll just be 1, but that's still 400,000 kilowatts an hour potential savings in energy. The cost would be $10,000 per heat exchanger, so a total of $90,000 for, the 8 or 9 cooling towers we have. And then, the heat exchangers. And then with that, you have a potential energy savings of 800,000 kilowatts an hour, which in dollar terms is 44 grand. And the ComEd would be offering an incentive of 7 cents per kilowatt an hour, so with a total of $56,000. So that would make our upfront payment roughly $36,000 to implement this. And this offers a simple payback of less than a year. So just a brief summary of those potential savings, because I know those numbers kind of being thrown everywhere. As far as electricity, 800,000 kilowatts an hour, 44 grand on your energy consumptions. And as far as water savings, it's not much. It's 4,992 gallons per minute. That's a lot, but in BASF terms and how much we go through on a daily, it wasn't even worth calculating the water savings. So, but in total, just the water that we could save through these several mechanisms, you would save money on the back end by not having to treat this water again. And to treat the water costs a lot more than the actual water itself. It's roughly about $7 to treat the water per 1,000 gallons. So this offers a $200,000 savings when it comes to water we would not have to send back to Kankakee to treat. And so just in total, with the cooling tower savings, the boiler tower savings, and then the ComEd savings, and as well as the wastewater savings, we're looking at about $300,000 worth of potential savings. And that's 56 million gallons per year, 800,000 kilowatts an hour. So yeah, with that, do we have any questions at all? Yes, ma'am.
This is a small question,
Mm-hmm.
but on one of your earlier slides, you had a bullet point that said hydrolysis reaction. And I know that term, hydrolysis, in terms of my hiking boots deteriorating.
Yes.
I don't know how you mean it.
Oh, I believe that was on that slide. It was one of the additional water usages for areas as far as cleaning, I believe. I'll check it out.
Was the last bullet on whatever. There.
Yeah, hydrolysis reactions. And this is just a chemical combustion, like just a chemical process. It is, I literally just looked this up. But yeah, we have estrogen reactions and a hydrolysis reaction, and I believe this is basically just adding, I don't want to elaborate too much, but I just put it in the biweekly report a few weeks back. But it escapes me at the moment. I'm terribly sorry. Yeah. Yes, ma'am.
I was just curious, on the schematic you had that you said you drew in the PowerPoint
Mm-hmm.
presentation, what exactly are like the lines and what are
All right. Let me see.
in the area?
All right. Well, yeah. So the lines depict the flow processes and where it's going and the directions. So generally, it started right here, and these are a ton of tanks and pumps and different chambers and heating mechanisms that it goes through before it actually leaves. And it's kind of compressed onto one page, but these buildings may be 2-3 stories. So I grabbed this information from our database that we have, so I was able to look it up from there and redraw it, by eyeballing it. And yeah, this is one of 23 of the drawings. Yes, sir. If that answers your question, I'm sorry. All right.
Some of the white boxes, I think, are the water streams. There's more than just the water streams on these drawings. Some of the boxes are the water streams that equate to this next slide that shows the water is coming in and out.
Yeah. Yes.
So for the cooling towers, you're saying that the water pumps are flowing at too fast of a rate?
It's just inefficient. For the cooling towers, it would just be a matter of recycling water, or like creating an open flow system versus a closed, where it would run through one time and then be sent to waste. Whereas if you were to implement an open flow system where the water is constantly cycling over and over again, because the whole purpose of a cooling tower is just to cool the hot water. So if we just keep reusing that same water and just filter it and recycle it, you would only have to add a small amount of water on top of that just to keep the temperature where you want to keep it at, versus one time and sending it back to Kankakee. Yes, ma'am.
How likely is it that they'll implement your?
See, and that's the thing I would like to talk to Mr. Reese about, because I would honestly have to spend a lot more time there. Not a lot more time, but just to get an understanding of where we're at and how much it would even cost to let's say implement these versus the savings, so we can calculate a simple payback period. Generally, BASF likes to keep their paybacks under 3 years. So if it's not in that favor, it may not be likely at all, unless it was just getting to a point where, all right, we have to do something, because we're swarmed with projects. Since day one, it's been towers being rebuilt, tanks being rebuilt. road construction. It's always something going on. It's a pretty old site, so I would really have to be able to quantify and put a numerical, a dollar amount on how much it would cost to implement, and then compare it to the savings. Yes, sir.
If it's a three-year simple payback or less, it'll be on our capital plans.
Yeah. Yes. Anybody else have any questions or concerns, comments? Yes, sir.
Well, you're just saying. So you're saying the simple payback you came up with here doesn't quite cover all the costs.
Oh yeah, no. That's that 0.8 simple payback was just for that one idea, which is installing the temperature controls. That was the only one that was quantifiable, and you can actually calculate. But everything else, because I don't know the current or existing conditions with these tanks, and to compare it to, I would really need to bring out a specialist, and that's beyond me at this point. So, yeah.
Do you have any idea what the cycles of concentration were for those cooling towers?
The cycles.
The cycles of concentration, how many times was it going through that system before I know you got a makeup water coming in.
Yeah.
You got blowdown.
Correct.
In that system. Looks like you got a lot of evaporation.
Yes, it's a ton of evaporation. There's a lot of blowdown. So I mean, basically, with the recycling mechanism, it would reduce your blowdown concentration by 20%. But with the initial blowdown it literally goes through once and off into waste streams.
We do have those for each tower, and it's drastically different from tower to tower depending on the issue production.
Well, yeah.
Less than one, and some are up to 5 or 6 or so.
Yeah, I think an optimum would be around 3 or 4 if you could get there. So.
Anybody else? Well, all right. Thank you for your time.